Today we are going to discuss about the basic properties of polymers. Previously we have already discussed about the metals and their alloys and the ceramics. So, today we are going to discuss the third part of this particular lecture series, that is polymers. So, this we have already shown in our previous lectures that we have already done the metals and their alloys, we have done the ceramics, and today we are going to discuss about the polymers. So, before going to start, first let us know that what is polymers. So, the word polymers, it is generally divided into two parts, one is called the poly, another one is called the mer. Poly means, as we know, it is many, and the mer means unit. That means there is some repeating unit generally we are using, or maybe some repeating units are present, that is why it is called the polymer. Generally it is defined as a very large molecules having high molecular mass, generally 10 to the power 3 to 10 to the power 7 unit, and referred to as macromolecules. The macromolecules are formed by the repeated linking of small unit called the monomers, as I told already. So, small monomers, they are attaching each other, and then after that they are making one polymers. Monomers are linked to each other by the covalent bonds. So, generally in polymer we can see the covalent bonds. A single polymer molecule may consist of hundreds to a million monomers and may have a linear, branched and the network structure. So, the example of the polymers like transformations of the ethane to the polyethane. So, ethane here is a single monomer, then we are doing the polymerizations, then that means same monomers is attaching ethane all together, and then after that they are making the polyethylene polymer. So, what are the classifications of polymer? So, generally we can do the 5 broad classifications of the polymer. First one is that based on source, then based on structure of polymers, based on mode of polymerizations, based on molecular forces, and the based on polymerization mechanism. So, first based on source, it is also divided into 3 parts, one is called the natural polymers, semi-synthetic polymers and the synthetic polymers. When you are talking about the structure of polymers, it is also divided into 3 parts, one is called the linear polymers, branched chain polymers and the cross linking polymers. When we are talking about the how we are preparing the polymers, then that means the mode of polymerizations, it is called the addition polymers and the condensation polymers. And then when we are talking about the molecular forces, it is also divided into some parts, that is elastomers, fibers, thermoplastic polymers, thermosetting polymers, and polymerization mechanism, it is also divided into 2 parts, that is addition or chain growth polymerizations and the condensation polymerization. So, first we will discuss all one by one. So, we will start with the based on the sources. So, under this type of classifications there are 3 subcategories, one is called the natural polymers. Natural polymers means which we are getting from the environment, that means they are derived from the plants and the animals. What are the examples? Examples is like wood, rubber, cotton, wool, protein, enzymes, silk, etc. So, these all are we are directly getting from some plants or maybe some animals. Now, semi-synthetic polymers, generally cellulose derivatives such as cellulose acetate, which is known as the rayon, and the cellulose nitrate. There are some synthetic polymers also. So, synthetic polymers, these polymers are synthesized in our industry or maybe the lab from the chemical substances. So, mainly we are preparing this kind of polymers as per our requirement. They are man-made polymers extensively used in daily life and industry. What are the examples? Examples like plastic, polyethylene or maybe polythene, and synthetic rubbers like Buna S, and the synthetic fibers like the nylon 66. Now, we are going to discuss about the classifications based on structure of polymers. So, first it is called the linear polymers, which consist of a long and straight chain like high density polythene, polyvinyl chloride. So, in this particular case you can find that there is a long chain of all the mers. Then we are talking about the branch chain polymers, contain linear chains having some branches. In this particular image you can see there is certain branches has been attached with the main chain, like example is low density polythene. And when we are talking about the cross linked or maybe the network polymers, so from this you can find they are forming some kind of bifunctional or maybe the trifunctional monomers, and the contain strong covalent bonds between the various linear polymer chains. So, it is one polymer chain, it is another polymer chain, in between that they are making some linkage or maybe the cross linking. Examples: bakelite and the melamine. Now, we are going to discuss about the classification based on mode of polymerizations. So, polymer also can be classified on the basis of mode of polymerizations into two subgroups, as I already told you. One is called the addition polymers. From the name itself we can understand that it can be formed by repeated addition of monomer molecules possessing the double or maybe the triple bonds. So, two types of addition polymers, one is called the homopolymers, another one is called the copolymers. So, what is homopolymers? They are made by single monomeric species polymerizations. Example: formation of polythene from the ethane. The same group we are attaching all together like a monomer, and then we are getting the polymer itself. So, from ethane we are making the polythene, and in this particular case when we are talking about the copolymers, they made by addition polymerizations from two different monomers. So, there are two species generally we are adding and we are making these polymers, like if we add the styrene with 1,3-butadiene, then we can get the BuNa-S. Next, we are going to discuss about the condensation polymers. So, formed by the repeated condensation reactions between two different bifunctional or maybe the trifunctional monomeric units. In these polymerization reactions, the eliminations of the small molecules such as water or maybe alcohol or maybe hydrogen chloride etc. takes place. So, what is the examples of the condensation polymers? Like nylon 6, terylene, nylon 6,6. So, how generally we are making? We are adding adipic acid with the hexamethylene diamine, and then we are making the nylon 6,6 and the water, and then after that we are removing this water and we are getting the nylon 6,6. Then classification based on molecular forces. So, on the basis of magnitude of the intermolecular forces present in them, divided into four subgroups. What are those? First one is called the elastomers. Elastomers is nothing but the rubber. So, it is a rubber like solid with elastic properties. Polymer chains are held together by the weakest intermolecular forces. Weak binding forces causes the polymer stretching. So, we can stretch it up to certain limit. What are the examples? Like neoprene, BuNa-S, BuNa-N. Generally, when we are using this kind of elastomers, so we are adding with some fillers or maybe some kind of additives. Say for example of the tire, we are adding natural rubber with the styrene butadiene rubber. Then how generally this is taking place? So, this is the taking place, the term is called by vulcanizations. What is vulcanizations? Generally cross linking process in which rubber molecules are converted into 3D network of interconnected polymer chains through chemical cross linking of sulfur. Here we have given only the sulfur, generally we are doing the vulcanizations by the hydrogen peroxide also. So, simple, in between the polymer chains we are making the cross linking of that and we are making this kind of materials. Then next is the fibers, thread forming solids which possess high tensile strength and high modulus, have strong intermolecular forces like hydrogen bonding, which leads to close packing of the chains and crystalline in nature. What are the examples? Like polyamides, nylon 6,6, polyesters or maybe known as the terylene. Next, we are going to discuss about the thermoplastic polymers. So, generally these polymers are linear or maybe the branched long chain molecules capable of repeatedly softening on heating and hardening on cooling, possess intermolecular forces of attractions intermediate between elastomers and the fibers. So, in a basic idea I can tell you that thermoplastic polymers is something like that, that if we give a shape and then after that we can give it heat and it can again melt and again we can give it the heat. So, it is not the permanent one, but when we are talking about the thermosetting polymers, it is like a, if we give a shape particular shapes, after that we cannot change it. So, cross linked or branched polymer molecules which on heating undergo extensive cross linking in molds and again become infusible. these cannot be reused. That is the vital point for the thermosetting polymers. So, what are the examples? Examples like bakelite, urea, formaldehyde resins, etc. So, generally if we see the whole order of strength of this kind of materials, so first thermosetting, then after that fibers, and then after that thermoplastics, and last is the elastomers on the strength point of view. Next we are going to discuss about the classification based on growth polymerizations, means mechanisms. So, there are two types of polymerizations reactions generally taking place. First one is called the addition polymerizations, second one is called the condensation polymerizations. What is addition polymerizations? Sometimes it is known as the chain growth polymerizations also. So, in this particular case, polymer is formed from monomer without loss of any material. Product is exact multiple of original monomeric molecules. Proceeds by initial formation of some reactive species like free radicals or ions, and by the addition of reactive species to other molecule with regeneration of reactive features. What is free radical mechanisms? Alkanes are polymerized in presence of free radical generating initiator, or which is known as the catalyst also. Initiator like benzoyl peroxide, acetyl peroxide, tertiary butyl peroxide, etc. are acting as an catalyst. There are three steps of free radical mechanisms. First one is called the chain initiation step, second one is called the chain propagation step, and third is called the chain terminating step. So, what is chain initiation step? In this particular case we can see that involves addition of phenyl free radicals formed by peroxide to ethane double bond and forms the larger radicals over here. So, first it was benzoyl peroxide, then benzoyl free radical we are making, then phenyl free radicals, and then we are using the with the ethane as a monomer. When we are talking about the chain propagation step means whatever product we have prepared, now we are try to increase the growth of that particular mass. So, what is that? Repetition of this sequence with new and bigger radicals. So, like ethane, so repeating unit, then again we are going to increase the same repeating unit, and then last one is called the chain terminating steps, means after certain time, after certain reaction we are going to terminate the whole process. So, product radicals thus formed reacts with another radical to form the polymerized product. So, ultimately we are making the polythene. Now, we are going to discuss about the some important addition polymers, how we are going to prepare. Say suppose we are going to discuss about the polythene. It is widely used polymer and of two types. One is called the low density polythene, another one is called the high density polythene. Low density polythene, sometimes we are calling it as a LDPE. So, what is that? Have numerous branches and so hard to compress, polymer chains packed loosely together, more flexible and lightweight, has low crystalline and high amorphous regions, has weaker intermolecular forces and tensile strength, it is less chemically inert. So, like example, like the squeeze bottles generally we are using for the chemical reactions, because it should not be very hard, so that we can squeeze it and the water will come out. When you are talking about the high density polyethylene, in short it is called the HDPE. So, it is having some linear structure, so can be compressed, polymer chains packed more tightly, so strength is more, less flexible and stronger, has high crystalline and low amorphous regions, has stronger intermolecular forces and the tensile strength, and it is chemically inert also. What are the examples? Examples is the pipes. These pipes generally we are using for the wiring applications in our household. Next we are going to give the examples of the polytetrafluoroethylene. So, polytetrafluoroethylene is also known as the Teflon. It is manufactured by heating tetrafluoroethane with a free radical or maybe the persulfate catalyst at high pressures. What are the properties? Generally it is chemically inert, it is resistant to attack by the corrosive reagents. So, uses in generally making oil seals and gaskets we are using, for the non-stick surface coated utensils generally we are using. So, nowadays in our kitchen we are using all the non-stick utensils where we are using the coating of these Teflon materials. So, tetrafluoroethylene in the presence of catalyst and high pressure we are making it the Teflon, we are using it for the non-stick pan. Then we are going to discuss about the polyacrylonitrile. So, addition polymerizations of acrylonitrile in presence of a peroxide catalyst leads to the formation of polyacrylonitrile. What are the uses? Used as a substitute for the wool in making commercial fibers as Orlon or maybe the Archilan. So, sometimes it is called the synthetic wool also. So, acrylonitrile in the polymerizations in the presence of peroxide catalyst, we are making the polyacrylonitrile. Next, we are going to discuss about the condensation polymerizations. What is that? It involves a repetitive condensation reactions between two bifunctional monomers, results in loss of some simple molecules like water or maybe the alcohol, etc. It leads to formation of high molecular mass condensation polymers. It is also called as the straight growth polymerizations. So, sometimes condensation polymerizations is also known as straight growth polymerizations. What are the examples? Formation of pterylene by the interaction of ethylene glycol and the terephthalic acid. So, ethylene glycol, terephthalic acid, it is making the pterylene or maybe the dacron. So, here other examples of the condensation polymers are melamine polymer. So, generally we are using for some crockery or maybe some cups, we are using some kind of bakelite polymer, we are using polyamide like nylon 6,6, nylon 6, and we are using some polyester like toluene or maybe the dacron. Next, we are going to discuss about the preparation of some important condensation polymers. So, what is that? It is called the polyamides, which possess the amide linkages and an important example of the synthetic fibers as nylons. Product of condensation polymerizations of diamines with dicarboxylic acids and also of amino acids and their lactams. So, how we are preparing the nylon? So, first nylon 6,6 we are preparing. So, product of condensation polymerization of hexamethylene diamine with adipic acid under high pressure and the temperature is almost 553 Kelvin. So, we are making nylon 6,6 as a byproduct. H2O means water is also generating. So, what are the uses? In making sheets, in bristles for brushes and in the textile industry. Then how we are making the nylon 6? Obtained by heating the caprolactam with water at high temperature. So, caprolactam in the presence of water at temperature varies from 533 to 543 Kelvin. So, we are making the nylon 6. What is the uses? Generally in manufacture of tire cords, fabrics and the ropes, we are using the nylon 6. Then another example is the polyesters. So, polyesters from the name itself we can assume that generally polycondensation products of the dicarboxylic acids and the diols. So, it is manufactured by heating a mixture of ethylene glycol and the terephthalic acid at 420 to 460 Kelvin in presence of zinc acetate antimony trioxide catalyst. What are the examples? Like dacron or maybe the pterylene. Pterylene is some kind of materials generally we are using for our shoots or maybe dress materials, and it is crease resistant. What is the use of that materials? The in blending with cotton and the wool fibers at glass reinforcing materials in the safety helmets. Next, we are giving the examples of phenol formaldehyde polymers, which is nothing but known as the bakelite. So, condensation product of phenol with formaldehyde in presence of an acid or maybe the base catalyst. Novolac is the best example, which is nothing but the initial and linear product. So, Novolac nowadays it is using in paints. On heating with formaldehyde undergoes cross linking to form an infusible solid mass called the bakelite. It is used for making the combs, phonograph records, electrical switches and handles of the various utensils. It is very hard and it is also the temperature resistant materials. So, how we are making? We are taking the phenol formaldehyde and then we are adding with the bakelite and then we are making the bakelite products. So, simple phenol formaldehyde, by doing the condensation methods we are making the bakelite and water is coming as a byproduct materials, and here we can see the several examples of the bakelite products. Next, we are going to discuss about the copolymerizations. So, copolymerizations, polymerization reactions in which a mixture of more than one monomeric species is allowed to polymerize and to form a copolymer. Copolymer can be made not only by chain growth polymerizations, but by step growth polymerizations also. So, in a different step one by one following, if you follow, and then we can make this kind of polymerizations. It contains multiple units of each monomer used in the same polymeric chain. So, what are the examples? Like mixture of 1,3-butadiene and styrene can form a copolymer. So, 1,3-butadiene with styrene, with some conditions we are making the butadiene styrene copolymer. Copolymers have properties quite different from the homopolymers. What are the examples? Butadiene styrene copolymer, it is quite tough, good substitute for the natural rubber. Sometimes we are using it for some other applications, used for manufacture for the auto tires, floor tiles and the cable insulations. Next we are going to discuss about the rubber. So, rubber generally it is two types, one is called the natural rubber, another one is called the synthetic rubber. So, natural rubber it is generally directly what we are getting from the plant itself. So, natural polymer and has coiled structure called as elastomer due to the elastic properties. Linear polymer of isoprene, which is nothing but the chemical name is 2-methyl-1,3-butadiene, also called as cis-1,4 polyisoprene. Cis polyisoprene molecule consists of various chains held together by weak van der Waals interactions, because forces are very less over there. As I told already, so vulcanizations of rubber means when we are adding 2 or more rubbers, and then in between that we are using some cross linking materials like the hydrogen peroxide or maybe the sulfur, and then we are making one kind of polymeric chain over there. So, generally natural rubber becomes soft at high temperature, the temperature is more than 335 Kelvin, and brittle at low temperatures, generally it is less than 283 Kelvin. It improves the physical properties, shows high water absorption capacity, vulcanizations, also improves the soluble in non-polar solvents, and its non-resistance to attack by the oxidizing agent. So, here as I told already, we are adding the sulfur as a vulcanizing agent, and then we are making the vulcanized rubber over there, and here you can see that sulfur has been making a cross linking in between the polymeric chains. Next we are going to discuss about the synthetic rubber, which I have already told that generally we are making it in some by chemical reactions in our lab or maybe the industry. So, it is any vulcanizable rubber like polymer capable of getting stretched 2 twice its length. It returns to its original shape and size as the external stretching force is released. Its elongations is high. They are either homopolymers of 1,3-butadiene derivatives or maybe the copolymers of 1,3-butadiene. So, there are two types of techniques by which we can prepare these synthetic rubbers. First one is, or maybe the examples is like that, one is neoprene. So, formed by the free radical polymerizations of the chloroprene. So, chloroprene we are using the polymerizations, and from that we are making the neoprene. Where we are using this neoprene, generally we are using it for the conveyor belts, gaskets and hoses. And another example is that Buna N, generally obtained by copolymerizations of the 1,3-butadiene and acrylonitrile in presence of peroxide catalyst. Already I told, either generally we are doing the vulcanizations by the sulfur or maybe the hydrogen peroxide catalyst. So, resistance to the actions of petrol, lubricating oil and the organic solvents. That is why this Buna N generally we are using for oil seals, tank lining and etc. So, now we are going to discuss about the properties of polymers. So, if we divide all the properties, so generally there are 4 groups. First one is called the physical properties. There are 2 subgroups, one is the degree of polymerizations and molecular weight, another one is the polymer crystallinity. Next groups is thermal properties, which will tell us the melting point and the glass transition temperature of that particular polymer. And if we talk about the mechanical properties of the polymers, it is divided into 5 parts. One is strength, percent elongation to break, Young modulus, toughness, and another one is that viscoelasticity, and last one is the chemical properties. So, we will discuss all these properties one by one. So, first we are going to start with the physical properties. So, physical properties means the first molecular weight will come, degree of polymerizations will come, then crystallinity of polymer will come and the low density. So, these all are together is known as the physical properties of polymer. So, first degree of polymerizations and the molecular weight. So, first we have to know what is the degree of polymerizations. So, the number of repeating units in the polymer chain is known as the degree of polymerizations. What is the molecular weight of the polymer molecule? It is the product of the degree of polymerizations and the molecular weight of the repeating unit. Then what is the molecular weight averages? The polymer molecules are not identical, but they are a mixture of many species with different degree of polymerizations, that is with different molecular weights. So, how generally we are giving the mathematically we are giving it. So, it is generally the summation over I from 0 to infinity pi xi. What is the number average molecular weight? So, if Ni is the number of polymer molecules having the molecular weight Mi, then the number average probability of given mass is given by generally Pi is equal to Ni by summation of j from 0 to infinity Nj. What is Mn? Generally it is summation over I is equal to 0 to infinity into Ni by summation over j 0 to infinity Nj into Mi, that means is equal to summation over I is equal to 0 to infinity Mi Ni by summation over j 0 to infinity Nj. So, this is the another equations. So, what is the physical properties like transition temperature, viscosity, and the mechanical properties like the strength, stiffness and toughness depend on the molecular weight of polymer. Lower the molecular weight, lower the transition temperature, viscosity and the mechanical properties. This is the generally the standard rules we are following. Due to increased entanglement of the chains, means that the cross linking in between the chains with increased molecular weight, the polymer gets higher viscosity in the molten state, which makes the processing of the polymer difficult. Now, we are going to discuss about the weight average molecular weight. So, the weight average probability generally it is given by Pi is equal to Ni Mi by summation over j 0 to infinity Nj Mj. The weight average molecular weight is given by Mw is equal to summation over I to 0 to infinity into Ni Mi by summation over j 0 to infinity Nj Mj into Mi, which is nothing but the summation over I 0 to infinity Ni Mi square by summation over j to infinity Nz Mz. So, what is the degree of polymerizations? The degree of polymerizations can be calculated using the number average molecular weight, which is nothing but number average molecular weight by the molecular weight of the repeating unit. Now, we are going to discuss about the polymer crystallinity. From this particular slide we can get the information about the crystalline and the amorphous polymers. So, generally polymer chains are very large, as I already told you, and found in the polymer in two forms, as the lamellar crystalline, another one is called the amorphous. What is lamellar crystalline? In which the chains folds and make lamellar structure arranged in the regular manner, and what is amorphous? In which the chains are in irregular manner. So, lamellars are embedded in amorphous part and communicate with other lamellar via tie molecules. Polymers having high degree of crystallinity are rigid and have high melting point, but their impact resistance is too low. Amorphous polymers are soft and have lower melting points. So, generally if we going to calculate the percentage crystallinity, it is the formula is Pc into Ps minus rho c into rho s minus rho a by rho s into rho c minus rho a into 100, means when we are going to calculate the percentage. So, where rho c is the density of the completely crystalline polymer, rho a is the density of the completely amorphous polymer, and rho s is the density of the sample. Now, we are going to discuss about the thermal properties of the polymers. So, when we are going to do the any thermal characterizations, generally we will get two informations. First one is the melting point, another one is called the glass transition temperature. This is the unique properties of the polymers or maybe any kind of elastomeric materials. So, glass transition temperature is the property of amorphous regions of polymer, whereas the crystalline region is characterized by the melting point. So, that is why generally for the rubber or maybe the elastomers we are getting the glass transition temperature, or maybe any kind of polymer we are getting the melting point. So, glass transition temperature is the second order transitions, whereas the melting point is the first order transitions. The value of glass transition temperature is not unique because the glassy state is not in equilibrium. So, generally the glass transition temperature for natural rubber is minus 70 degree centigrade. Its value depends on several factors such as molecular weight, measurement methods, on the rate of heating or cooling. Now, we are going to give some examples of the semi-crystalline polymers, which shows both the transitions correspondence to their crystalline and amorphous regions, so have true melting temperatures at which the ordered phase turns to disordered phase, whereas the amorphous region softens over a temperature range known as the glass transition temperature. So, generally the semi-crystalline polymer example is that liquid crystal polymer, or maybe sometimes we are calling it as a LCP. So, in this particular case this is the temperature, this is the glass transition temperature Tg, this is the melting temperature Tm. So, glass transition for glass materials generally it varies up to the glass transition temperature, then it is rapidly increasing the volume. When you are talking about the semi crystalline it is quite less, and for the crystalline solids it is totally increasing in a rapid manner. So, amorphous polymers do not possess any melting temperature, as I already told you, but all polymers possess the glass transition temperature. Yes, of course, generally as a thumb rule the glass transition temperature of the polymer is around 10 to 15 degree. So, the polymer melting temperature point Tm is increased if the double bonds, aromatic groups, bulky or maybe the large side groups are present in the polymer chains, because they restrict the flexibility of the chain itself. The branching of chain causes the reduction of melting point, as defects are produced because of the branching. So, generally glass transition temperature of some polymers, as I told, like polytetrafluoroethylene it is minus 97 degree centigrades, polypropylene 100 degree centigrade, polystyrene 100 degree centigrade, nylon 66 is 57, polyethylene LDP is minus 120. So, these all are the different glass transition temperature for the elastomers and the polymers. So, what are the factor affecting the glass transition temperatures? So, first is intermolecular forces. So, strong intermolecular forces cause the higher glass transition temperature. Next one is called the chain stiffness. So, the presence of stiffening groups such as amide, sulfone, carbonyl, p-phenylene etc. in polymer chains reduce the flexibility of the chain, leading to higher glass transition temperature. Next is cross linking. The cross links between the chains restricts the rotational motions and raise the glass transition temperature. Hence, higher cross linked molecule will show the higher glass transition temperature than that with lower cross linked molecules. Next is pendant groups, means what are the groups are attached. The presence of pendant group can change the glass transition temperature. And last one is the plasticizers, low molecular weight and non-volatile material added to polymer to increase their chain flexibility, reduce the intermolecular cohesive force between the polymer chain, which in turn decreases the glass transition temperature. And another one is the molecular weight. So, the glass transition temperature is also affected by the molecular weight of the polymer. Tg is increased with the molecular weight. The molecular weight generally is related to the glass transition temperature by the Fox-Flory equations. So, what it tells, generally glass transition temperature is equal to Tg to up to infinity minus K by Mn, where Tg infinity is the glass transition temperature at all molecular weight of infinity, K is the empirical parameter called the Fox-Flory parameter. So, this one related to free volume inside the polymer. It is observed that the glass transition temperature is increased up to the molecular weight of approximately 20,000, and after this limit the glass transition temperature is not affected. Next, we are going to discuss about the mechanical properties. So, when we are going to discuss about the mechanical properties, first it will come the mechanical strength. So, it is the strength is the stress required to break the sample. There are several types of mechanical strength. First one is called the tensile, generally stretching of the polymer, torsional which is related to the twisting of the polymer, impact generally by the hammering, flexural bending of the polymer, and the compressional means the compression of the polymer. So, what are the increasing strength? So, in that particular case the increasing strength is like that, network is the highest one, then cross linked, then the branched, and linear is the lowest one. So, here if we see the stress strain curve of the polymers, so generally for the brittle plastic, then fiber and the elastomer you can see the maximum strain over there. So, in terms of stress, so fiber is the highest one. So, what are the factor affecting the strength of polymers? First one is the molecular weight, where tensile strength plays a vital role. So, tensile strength of polymer rises with increase in molecular weight and reaches at the saturation level at some value of the molecular weight. So, generally sigma is equal to sigma infinity minus A by m, where sigma infinity is nothing but the tensile strength of polymer with molecular weight of infinity, A is some constant, and capital M is nothing but the molecular weight of that particular polymer. Cross linking restricts motions of chain and increase the strength of the polymers. Crystallinity, it increases the strength, but because in crystalline phases intermolecular bonding is more significant, hence the polymer deformation can result in the higher strength leading to the oriented chains itself. So, here the variations of the tensile strength with molecular weight of the polymer. So, you can see that molecular weight and strength. So, if we are increasing the molecular weight up to certain time, the strength will increase, and then after that it will become constant. Now, we are going to discuss about the percentage elongations of break, or maybe known as the ultimate elongations. So, it is the strain in the material to its breakage. Suppose we are having one polymer, we are pulling it, then it will increase and increase and increase, after certain time it will frail. So, it measures the percentage change in the length of material before fracture. So, it is a measure of the ductility. Ceramics have very low, less than 1%, metals have moderate, generally 1 to 50%, thermoplastic is more than 100%, and thermosets is also less than 5% value of elongation to break. What is the Young modulus, or maybe the modulus of elasticity, or maybe the tensile modulus? It is the ratio of stress to the strain in the linearly elastic region. Elastic modulus is a measure of the stiffness of the material. So, generally it is denoted by capital E, which is nothing but the tensile stress sigma by the tensile strain, that is epsilon. Toughness. So, the toughness of a material is given by the area under a strain curve. It is measured the energy absorbed by the material before it breaks. What is the toughness? Generally it is the integration of 0 to epsilon f into sigma d epsilon, where epsilon f is the true strain at fracture. So, this is the whole toughness of these particular polymeric materials. So, from the stress strain curve is shown, which compares the stress strain behavior of different types of materials. From this you can see we have given the examples of the brittle polymer, we have given the examples of the ductile polymer, and we have given the high elastic. So, you can see what is the toughness of this particular material. So, rigid materials possess the high Young modulus such as brittle polymers, and ductile polymers also possess the similar elastic modulus, but with higher fracture toughness. Now, we are going to discuss about the viscoelasticity. So, there are two types of deformations generally we are seeing. First one is known as the elastic deformations, and the second one is called the viscous deformations. So, what is elastic deformations? Strain is generated at the moment the constant load or stress is applied, and the strain is maintained until the stress is not released. On removal of stress, the material recovers its original dimensions completely, that is, the deformation is reversible because it will come to again to its original positions. Sigma is equal to E epsilon, where E is the elastic modulus, sigma is the applied stress, and the epsilon is the strain developed. Then we are going to discuss about the viscous deformations. So, strain generated is not instantaneous and it is time dependent. When the load is removed, material does not return to its original dimensions completely. So, there is little bit stress will be present in the material. So, deformations is irreversible. So, generally sigma is equal to gamma into d epsilon by dt. So, where gamma is the viscosity and d epsilon by dt is equal to strain rate. So, but low strain rate polymers show combined behavior of elastic and plastic deformation depending on temperature and strain rate. At low temperature and high strain rate elastic behavior is observed, and at a high temperatures the viscous behavior is also observed. So, combined behavior of viscosity and elasticity is observed at intermediate temperature and the strain rate value. So, generally we are having one elastic behavior materials, when you are adding with some viscous behavior materials we are getting the viscoelastic properties of that particular materials. So, this behavior is termed as the viscoelasticity and the polymer is termed as the viscoelastic polymer. Now, we are going to discuss about the chemical properties of polymers. So, different side groups on the polymers can lend to ionic bonding, another one is called the hydrogen bonding. So, polymers containing amide or carbonyl groups can form the hydrogen bonds between adjacent chains. Dipole bonding is not as strong as the hydrogen bonding. Examples like polyesters have dipole bonding between the oxygen atoms C double bond O groups and the hydrogen atoms in CH groups. Generally polymeric materials are non-corrosive in nature because upon exposure to liquid they may experience by the swelling or maybe the dissolution. Polymers may deteriorate by the swelling and the dissolution, it is also another properties of the polymers. Now, we are going to discuss about the polymer degradations. So, it is a change in the properties like strength, color, shape, molecular weights etc. of polymer or polymer based products under the influence of one or more environmental factors such as heat, light, moisture or chemical. Say suppose we are keeping that polymer for a longer time into the environment or maybe buried into the soil or maybe dipping into the water. So, we can see the degradation of that particular polymer. So, covalent bonds in polymers are ruptured as result of the environmental factors. Due to chemical complexity of polymers, their degradation mechanisms are not well understood, still research are going on. Polymer can degrade by exposure to like high temperature, what will happen? Thermal degradation will take place. If it is under shear action, mechanical degradation will take place. If it is under oxygen, ozone and chemicals, the chemical degradation will take place. Electromagnetic, ultrasonic radiations, light induced degradation will take place, and if it is open to the moisture or maybe the liquid, hydrolysis or swelling or maybe the dissolution will take place. Now, we are going to just give a brief idea about the ceramic, metal and polymer in terms of different properties. So, say suppose if we talk about the hardness, ceramic is having very high, metal is low and polymer is also low. So, generally I will give you some major examples like elastic modulus. For ceramic it is high, for metal it is high, but for polymer it is also low. If we talk about the ductility, for ceramic materials it is very low, for metal it is high and for polymer also it is high. If we are talking about the electrical conductivity, so generally for the ceramic materials it is intermediate, for metal it is too high, but polymer it is low, generally it acts as a one kind of insulator. If we talk about the thermal conductivity, for ceramic it is intermediate, metal it is high, for polymer also it is very low. Now, what are the characteristics of the polymers? So, generally polymer is having low density, low coefficient of friction, good corrosion resistance, good mold ability, poor tensile strength, low mechanical properties and the poor temperature resistance. What are the advantages of polymers? Generally it resists to corrosions and the chemicals, low electrical and thermal conductivity can be made conducting, low density, high strength to weight ratio, that is the prime considerations for choosing the polymer. It can reduce the noise, it is a wide choice of colors and the transparencies, easy of manufacturing and complexity of the design possibilities, and also it is very cheap. What are the disadvantages of polymers? So, generally comparatively low strength and low dimensional stability, have low heat resistance, high performance plastics have very high cost, some polymers are very costly. They are softer than metals and are more susceptible to deformation under load. It is go brittle at low temperature and are also flammable, it can burn easily. So, now we are going to give some common applications of the polymers. So, generally for the sports we are using for some helmets, some balls, or maybe medical we are using some kind of tissue scaffolds, some bones, joints. Nowadays we are using some kind of orthopedic implants. For industry we are using some automobile parts, for using insulations, for packing materials. For agriculture we are using it for the preventing soil erosions, reducing the irrigation facility, and these all are the very less. There are n number of applications where we are using the polymer. So, now we have come to the end of this particular lecture, and if we summarize this particular lecture, we have already discussed that polymers are organic macromolecules made of repeating units. Material properties controlled by degree of cross linking. Different classes of polymers, and already we have discussed with their properties. We have discussed about the mechanical properties, thermal properties, chemical properties of those polymers, and it is also very easy materials to process and having the low cost. Thank you.